if something's not sitting right, stop me, we'll go through it. The next unit we start adding ands and ors, and it gets a little bit more confusing. I'm not sure where your backgrounds are in the probabilities, with all the course changes and everything, and it's probably been a while. My board hasn't been very cooperative today, so hopefully it will cooperate. All right, so number 29. You have a 12-sided die, which means you have 12 faces to this die. So 1 out of 12 is your probability for rolling each one of the faces. For rolling a number divisible by 3, look to see which numbers can be evenly divided by 3. Those are your multiples of 3. So 3, 6, 9, and 12. You have 4 possibilities out of 12. You can give it to me as a fraction. You can give it to me as 3 decimals. I kind of tend to do the decimals just because they're easier to compare, especially when your denominators are not the same. All right, you have given this table. You're asked to find what is the probability that the next person surveyed is very prepared. So the first thing you're going to do, take the total. Very prepared, 259 over your total, and bring it down to 3 decimals. So there's a 12% chance that the next person that walks up to you will be very well prepared. What is the probability that the next person surveyed is not too prepared? Take the not too prepared over the total and give me the 3 decimals. Again, this chart is a tricky chart. A very prepared, somewhat prepared, not too prepared, not at all prepared. They're kind of like overlapping. So when you give someone these categories, be real careful about them. Somewhat prepared and not too prepared. I wouldn't know which one to go to. I'm somewhat prepared and still not too prepared, right? So maybe I feel a little bit more positive about it. I go with the somewhat. A little less positive about it, I go with the not too prepared. So watch those categories. Classify your probabilities according to company records. Company records, not standards above all. Company records. The probability that a washing machine will need repair during a 6-year period, shrink this down a little bit. During a 6-year period is 0.10%. This is empirical because even this company's washing machine, the records will change every year, won't they? So they have to keep changing their probabilities. Probabilities that change are empirical. Probabilities that never change are theoretical, such as the probability of choosing 6 numbers from 1 to 40 that match exactly the 6 numbers are drawn. That probability will never change. That's a theoretical. An analyst feels, here's a good buzzword, feels that a certain stock's probability of decreasing in price over the next week is 0.75, 75%. This is their feeling in here. It's not just randomly saying, well, there's about a 75% chance that this is going to happen. He does a lot of work into this. That's why when you go to different forecasters, different analysts, different whoever's doing predictions, they're slightly different. They throw a little bit of their gut feeling in there. Good with that? Good with those 3? Okay. Here's a complement case. Event A is randomly choosing a resident who is not 15 to 29 years old. Now, if you added these all up, they add up to 193. Not 15 to 29, you can still go back and add up these and put it over 193. Or you can do 193 minus 20. This is the complement case. Complement with an 8. So 173 over 193. It's a little easier to do. Randomly choosing a resident who is not 14 years old or younger. 14 years old or younger, there's only one case like that. So again, if you wanted to add those all up, that's fine. If you wanted to take this, use the complement case, subtract it from 193. When you subtract it from 193, you get 155 over 193. The complement case is a nice one to use if you're only looking for one thing out of a whole bunch, even two things. Here's a probability experiment with rolling a die, a six-sided die, and spinning a spinner. It has 4 sections. Each one of them has a 1/4 chance of happening. Know how to do this. Remember to start with you. I don't care if you do the rolling the die first or you spin the spinner first. The outcomes will be the same. Do your counting principle first. I expect 6 sides on my die, 4 things on my spinner. I should get 24 in my sample space. Keep it to one letter or a number. So I go through, I roll my die. I can get 1, 2, 3, 4, 5, 6. These are my dice, my die rolls. Off my die, I spin my spinner. Red, yellow, green, blue. So each of them has a 1/6 times 1/4 has a 1/24th chance of happening. I should get 24 entries here. From my sample space, this is my sample space. All possible outcomes. So now when I do my probability, I go right to my sample space. The probability of rolling a 5 and the spinner landing on a blue, I want a 5. Here's my 5 column. There's my blue. 1 out of 24. Break your sample space as the major branches are broken. So this way they're easier to spot. Rolling a number less than 6, I want 1 through 5. I want these guys. And spinning a spinner landing on yellow, I want all the yellows in here. So I get 5 out of 24. They look at unusual versus not unusual. The cutoff for unusual is 5%. Anything less than 5% is unusual. More than 5%, we're okay. If you think back, and we didn't spend a lot of time with it, but if you think back to the normal curve, the little things at the end, so anything more than 95%, greater than 95% would also be unusual. They use the cutoff of 5%, just to say unusual versus not unusual. These are good problems. The access codes for a garage door consist of 3 digits. Lay out your 3 lines. Your digits are from 0 to 9. You have 10 possibilities. You could have a 0, 0, 0. You have a 9, 9, 9. Each one of these has 10. This is how many ways this happens. It's the large number. Here's the difference for probability. This one says, what is the probability that the first time I try this, I get the right code? How many right codes, correct codes are there to open your garage door? 1. So 1 out of this number. This is my probability. See the difference between ways and probability? If it says probability, your answer has to be between 0 and 1. It can't be 10,000, 11, 1 million. It can't be any of those. But that's what I need to get my bottom number here. What is the probability of not selecting it on the first try? Well, all of those other numbers are wrong, right? There's only one right one. So here is my complement case. I'm not going to add all those up and say there's 999 wrong answers, right? So 999 over 1,000, I use my complement. 1 minus that one. Or 1,000 minus 1, 999 over 1,000. Now you got to think about what the problem is asking. The garage codes, only one answer, one code is going to open that. The access codes consist of a letter followed by 4 digits. Lay out the pieces, a letter, digit, 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 digit. Then look what they want. Any letter can be used. So I have 26 things to choose from for my first one. Then the first digit cannot be a 0. So if I have 10 choices and I cannot use a 0, I have 9 possible things left, right? And then they told me the last digit must be even. Well, from 0 to 9, how many of these are even? 0 counts as an even number. So half of them are even, right? Half of them are odd. So I have 5 even numbers. 1, 2, 3, 4, 5. 5 possible answers. It would look the same if I was looking for odd. 5 possible odds. They didn't tell me anything about the middle 2, so I'm assuming they can be any of the 10. And what do I do with all of those numbers? I multiply. If I added them, I sure wouldn't get a whole lot of possible codes to use. So I multiply them. What is the probability now? If I know these are how many ways this can happen, probability says there's only going to be one correct access code. 1 over that. When you round, even though we say 3 decimals, you have to round to the first significant digit. So if you round to this, 0.00009. Round it to the first significant digit. The book, I think, rounded it to 10 because they rounded it to here. That's fine. Just round to a significant digit. And the very last one, we talked about the square yesterday, the Punnett square. A diagram that shows all the possible gene combinations and a cross of parents whose genes are known. They use the pink, the red, and the white, and they have to have equal possibilities. So what is the probability that they will be pink? 2 sections of pink out of 4, 1 section of red out of 4, 1 section of white out of 4. Good with these? If you're not, tell me. Tomorrow we add a little bit more into this.